Okay, in this problem here, we have a cafe serves sandwiches and cakes. Each customer will choose one of the following three options to buy only a sandwich, buy only a cake, or both sandwich and a cake. And the probability that a customer buys a sandwich is 0.72. Probability that a customer buys a cake is 0.45. So when I have these scenarios, whenever I see probability numbers, I usually like to put notation attached to it if possible. And so the probability of a sandwich I know is 0.72. The probability of a cake is 0.45. And I have to recognize that some of these 72% of the people are also buying a cake. And so what I see here is I see a Venn diagram. I have two regions. One is the sandwiches and one is the cake. And I know that it's only these three options here. There's no one that doesn't buy anything. So the outside region here is 0. So these three regions have to add up to a probability of 1. But when I look at those, already I know, because there's some of these sandwich people also eat cake. So when I add 0.72 plus 0.45, I get 1.17, which means if I subtract that from 1, the overlap region here is 0.17. Now, when I find the sandwiches, well, I know that the 72 and the 17, this blank plus 17 has to be 72. So if I subtract the 72 and the 17%, I end up with 0.55. And then this one here also is going to be 0.45 minus the 17, which is not asked for, but I'll do it anyway, is 28. And so both sandwiches and a cake means the overlap region. So the probability of a sandwich and a cake is what I'm looking for. The overlap is 0.17. The probability of only a sandwich, not sandwich, only a sandwich, only an S is going to be 0.55. Okay, moving forward though with this scenario, we're also told that it's known that 46% of the customers who are coming are male. So the probability of being male is 0.46. Hence the probability of being female is 0.54. And then we're told that 80% of these, well, that's talking about the males, 80% of the males, or 80% of these, buy a sandwich. So it's the probability of a sandwich is what we're looking at, given that they were males, is going to be 0.80. And we want a customer is selected at random, find the probability that the customer is male and buys a sandwich. So we're asked to find probability of male and sandwich. Well, I know from my formulas the probabilities of sandwich given male is equal to probability of male and sandwich over the probability of male. And I always remember that this kind of looks like a fraction even though it's not, and so the m is on the bottom of the fraction, just a little memory tip. So I'm looking for this top value. So if I go 0.8 is equal to the probability of men and sandwiches over the probability of males, I clearly can see that my males and sandwiches is 0.8 times the 0.46, which will give me times 0.46 is 0.368. So that is the first part there. The second part then says a female customer is selected at random. Find the probability that she buys a sandwich. Well, looking at that one, so I want to find the probability that she buys a sandwich given that she's a female customer. So this is sandwich given female. Well, then I know if I'm going to do this, it's going to be the probability of a female and a sandwich over the probability of a female. Well, probably a female, and we know this value. Probably a female and a sandwich. Well, we have to go back further in the problem where we recognize the probability of getting a sandwich is 0.72. Okay, so the probability of a sandwich, the probability of just a sandwich is equal to 0.72. I know that if I draw a tree diagram here, that this is a male and this is a female. This is 0.46 and 0.54. I can buy a sandwich or I can not buy a sandwich. I can buy a sandwich or I can not buy a sandwich. I know that if I take this branch and this branch together, those two branches, they have to add up to 0.72 because these are the only ways to get sandwiches. I know that this particular branch is the probability of F and S, and this branch is M and S. That's how these work. Together, when I add them up, I have to get this value here. So let me not put that right here. What I do know, I figured out males and sandwiches is equal to 0.368. When I add them up, I said it's got to be 0.72. So 0.72 minus the 0.368 is 352. So this is 0.352. So probably of females and sandwiches is 0.352 over the probability of females is 54, 0.54. Oh, I put it in the wrong spot. 0.54, and when I do that computation divided by 0.54, I see that my probability of getting a sandwich, given that I'm a female, is 652 to 3 significant figures. So there's a lot of pieces to put together in this problem. We have to recognize that getting sandwiches can be males and sandwiches and females and sandwiches, and together they have to add up to the total number of sandwiches. Because we have the one, we can then go and find the other. Using our formula for conditional probability, we can see that we've come up with the correct probability. Finally, C part. We know that on her way to work, Ria stops at a cafe at 8 o'clock. The probability that she buys a cake is 0.45. So she goes to the store and she gets a cake, 0.45. Or she doesn't get a cake, which is then 55%. Okay, and we're looking for the probability that she can buy a cake first. So if she buys a cake, we're done. But it's possible that she doesn't buy a cake, and then at 8:30, Lila comes in, and Lila either buys a cake or she doesn't buy a cake. This we know is 0.6 that she buys a cake, 0.4 that she doesn't. So this happens. The next one that happens, though, is if she doesn't buy a cake, Ria could come in the next day and buy a cake or not buy a cake. And then Lila comes in, again, cake, no cake, which is 0.6, 0.4. And then Ria comes in, 0.45, 0.55, cake, no cake, and so on and so on and so on and so on and so on. So it is theoretically possible that no one will ever buy a cake between Lila and Ria. And so, but we want to find a probability that Ria buys a cake first. So that means we want the probability that Ria is first. Okay, for Ria to be first, well, we could have the simple scenario where she just walks in and she eats a cake. Or we could go here and she buys a cake. Because if she's going to be first, Lila cannot buy a cake. If she doesn't buy a cake and she's going to be first, Lila doesn't buy a cake and she doesn't buy a cake, Lila still can't buy a cake and she can buy a cake on this time. Right? She could go all the way here and then this branch. and so on and so on and so on. It goes on forever. And so Rhea being first, the first branch is 0.45. That's the first way. Or it could be on this one over here where she goes 0.55 times 0.4 times 0.45. That's the success. The next one is going to go 55 times 0.4 times 0.55 times 0.4 times 0.45. So it's 0.55 times 0.4 squared and then times 0.45. And that is going to continue on forever. And what you're recognizing, hopefully, is that this is the sum of an infinite geometric series, which we want u1 over 1 minus r. Well, u1 is 0.045. R is going to be the 0.55 times 0.4, which is the probability of both of them not choosing a cake. And when I put that all into my calculator, 0.45 divided by 1 minus 0.55 times 0.4, I get 0.577 to 3 significant figures. So in this problem, you have to recognize that this could go on forever and that no one ever buys a cake, and we're looking for Rhea buying the cake first.